Revolutionary discovery of potential biosignatures on K2-18b, a new era in the search for extraterrestrial life. On April 16, 2025, astronomers announced a groundbreaking discovery regarding K2-18b, an exoplanet located approximately 120 light-years away in the constellation Leo. This revelation marks a pivotal moment in the search for extraterrestrial life, as scientists have identified potential biosignatures in the planet's atmosphere, leading to unprecedented excitement within the astronomical community. Overview of K2-18b. K2-18b is classified as a Hycean planet, a term coined by Dr. Niku Madhusudhan and his team at the University of Cambridge. Hycean planets are characterized by their warm oceans and hydrogen-rich atmospheres, suggesting they could harbor life. K2-18b has drawn interest since its discovery by Canadian astronomers in 2017 due to its unique atmospheric composition, which researchers believe could support biological processes. Key findings: 1. Chemical signatures, utilizing the James Webb Space Telescope. Scientists detected significant amounts of dimethyl sulfide DMS and dimethyl disulfide DMDS in the atmosphere of K2-18b. On Earth, these compounds are primarily produced by marine algae, suggesting a potential biological origin. The presence of methane and carbon dioxide was also noted, contributing to the hypothesis of biological activity. 2. Atmospheric analysis. The analysis of K2-18b's atmosphere involved observing the starlight filtered through the planet's atmosphere as it transits its host star. The unique absorption patterns of specific wavelengths indicated the presence of the aforementioned compounds, leading researchers to infer the possible existence of life-supporting environments. 3. Cautious optimism. Despite the thrilling implications of these findings, the scientific community urges caution. Dr. Madhusudhan emphasized that while the evidence is compelling, it does not constitute definitive proof of life. Other researchers, including Stephen Schmidt from Johns Hopkins University, echoed this sentiment, noting that geological or chemical processes could also explain the observed compounds. Historical context: 2017, discovery of K2-18b by Canadian astronomers using ground-based telescopes. 2021, introduction of the Hycean planet concept by Madhusudhan's team. 2023, initial detection of DMS and other carbon-bearing molecules using the James Webb Space Telescope. April 2025, comprehensive analysis confirming the presence of DMS and DMDS published in the Astrophysical Journal. Reactions from the scientific community. The announcement has sparked a wave of excitement and curiosity among scientists. Dr. Madhusudhan described the moment as revolutionary, marking the first time humanity has glimpsed potential biosignatures on a habitable planet. He remarked, "Decades from now, we may look back and recognize this as the tipping point in our understanding of the living universe." Christopher Glane, a planetary scientist, stressed the need for further research to ascertain the habitability of K2-18b. He pointed out that without direct evidence of life, the findings remain speculative. The consensus among experts is that while the data collected is promising, more observations and experiments are necessary to confirm these initial findings. The broader implications. The implications of this discovery extend far beyond K2-18b itself. If confirmed, it could reshape our understanding of life in the universe and the conditions that support it. The ongoing research into Hycean planets could open new avenues for exploring other potentially habitable worlds. As the James Webb Space Telescope continues its mission, astronomers anticipate gathering more data that could clarify the conditions on K2-18b and the nature of its atmospheric compositions. Future observations may help distinguish between biological and non-biological sources for the detected chemicals. Conclusion: the findings regarding K2-18b represent a significant leap in the search for extraterrestrial life, bringing us closer to answering one of humanity's oldest questions: are we alone in the universe? While the evidence of potential biosignatures is compelling, extensive follow-up studies will be essential to confirm the presence of life and to understand the complex environmental conditions on this fascinating exoplanet. The scientific community remains hopeful yet grounded in the reality that definitive proof may take time and further exploration. As we embark on this new chapter in astronomy, the quest for life beyond Earth continues, fueled by curiosity and the promise of discovery. The recent discovery of potential biosignatures on the exoplanet K2-18b has sparked significant excitement within the scientific community, with some researchers heralding it as a revolutionary moment in the search for extraterrestrial life. However, several elements of this situation present counterintuitive insights that merit careful consideration. 1. Presence of life indicators versus life confirmation. While the detection of dimethyl sulfide DMS and other chemical signatures associated with biological processes on Earth is intriguing, it does not equate to the confirmation of life. This distinction is critical. The scientific community has not found definitive evidence of life, but rather indicators that could also arise from abiotic processes. For instance, while DMS is strongly linked to marine algae on Earth, scientists caution that geological or chemical reactions may also produce similar signatures. This leads to the counterintuitive understanding that promising biosignatures do not guarantee the existence of life, which is often the narrative that captures public attention. 2. Cautious optimism versus media sensationalism. Media coverage tends to amplify positive findings, sometimes obscuring the nuanced reality of scientific interpretation. For example, Dr. Madhusudhan's declaration of this moment as a pivotal point in humanity's quest for extraterrestrial life is indeed compelling, yet it stands in stark contrast to the measured skepticism expressed by other scientists such as Stephen Schmidt and Christopher Glane. They highlight that while the data is exciting, it is merely a hint, not conclusive evidence of habitability or life. The counterintuitive takeaway is that the scientific process thrives on cautious optimism and skepticism, even when faced with tantalizing discoveries. 3. Hycean planet concept. The classification of K2-18b as a Hycean planet, an idea suggesting that these exoplanets could support warm oceans and life-supporting atmospheres, introduces another layer of complexity. While this classification is based on theoretical models, it implies a certain expectation of what such planets should contain. The counterintuitive aspect here is that despite the existence of a model predicting oceanic conditions conducive to life, actual observations may reveal quite different environments, such as a massive rock with a scorching hydrogen atmosphere which would be inhospitable to life as we know it. 4. Discovery process and technology limitations. The reliance on advanced technology like the James Webb Space Telescope JWST to analyze distant exoplanets represents a double-edged sword. While JWST enhances our ability to detect faint signals, it also underscores the limitations of current methodologies. The counterintuitive insight is that as our tools become more powerful, the potential for misinterpretation or overinterpretation of data increases. The findings from K2-18b exemplify this, where initial excitement over detected biosignatures must be tempered with the understanding that further research is necessary to validate these readings. 5. Public perception and scientific reality. The notion that humanity might not be alone in the universe is a powerful narrative that captures the public imagination. However, the scientific reality is much more complex and less certain. The excitement around K2-18b's findings can lead to inflated expectations regarding the discovery of extraterrestrial life. This presents a counterintuitive situation where the more we learn about the universe, the more we might realize how little we actually understand about life and its myriad forms. Consequently, while the search for life is a thrilling endeavor, it is also fraught with ambiguity and uncertainty. 6. Long-term research perspective. Finally, the timeline for understanding K2-18b and its potential habitability is expected to be lengthy. The research community acknowledges that definitive answers may take years or even decades to uncover. This contrasts sharply with the urgency often portrayed in media narratives surrounding such discoveries. The counterintuitive aspect is that significant scientific breakthroughs are often incremental, requiring patient, sustained investigation rather than swift conclusions based on initial findings. Conclusion: the exploration of K2-18b and the implications of its atmospheric composition highlight numerous counterintuitive dynamics within the scientific process and public discourse. While the search for extraterrestrial life is indeed a groundbreaking endeavor, the realities of scientific inquiry remind us that excitement must be tempered with skepticism, and discoveries often prompt more questions than answers. In this era of rapid technological advancement and exploration, it remains critical to navigate the space between hope and evidence with care and diligence. The recent findings regarding K2-18b mark a pivotal moment in the quest for extraterrestrial life, and while many aspects have been highlighted in various reports, certain significant elements often go unnoticed. Below are key points that merit attention due to their implications for our understanding of life beyond Earth. 1. Chemical signatures and their implications. The detection of dimethyl sulfide DMS and dimethyl disulfide DMDS is particularly noteworthy. While many reports mention these compounds as potential indicators of life, the significance lies in their exclusive association with biological processes on Earth. DMS is primarily produced by marine algae, and its presence on K2-18b suggests a thriving biosphere. Significance: this detection challenges our understanding of what constitutes biosignatures. If DMS is confirmed to be abundant on K2-18b, it could lead to broader definitions of life and its markers in the universe. It raises the possibility that other planets may harbor life forms that produce entirely different biosignatures than those found on Earth. 2. Hycean planet concept. The classification of K2-18b as a Hycean planet, characterized by warm oceans and hydrogen-rich atmospheres, is significant as it expands the framework for identifying habitable worlds. This concept, proposed by Dr. Madhusudhan and his team, suggests that many previously overlooked planets might be capable of supporting life. Significance: this redefinition of potentially habitable worlds could lead to a paradigm shift in exoplanet research. Scientists may begin to focus on a broader range of celestial bodies, encouraging exploration of atmospheres and conditions previously deemed inhospitable. 3. Cautious optimism and scientific responsibility. The scientific community's cautious optimism is often overshadowed by excitement. Researchers like Stephen Schmidt and Christopher Glane emphasize the importance of not jumping to conclusions regarding the habitability of K2-18b. Significance: this stance underscores the ethical responsibility scientists have to the public when discussing discoveries that could reshape our understanding of the universe. The distinction between potential and confirmed life is crucial in maintaining scientific integrity and ensuring that future findings are based on robust evidence rather than speculation. 4. Technological milestones in future research. The role of the James Webb Space Telescope JWST in these findings cannot be overstated. Its advanced capabilities have allowed astronomers to detect molecular signatures in distant atmospheres with unprecedented precision. As the JWST continues to observe K2-18b, further discoveries may emerge. Significance: the JWST represents a technological leap that could revolutionize our search for life. Its ability to analyze the atmospheres of exoplanets will likely lead to more discoveries of potential biosignatures, thereby enhancing our comprehension of the conditions necessary for life. 5. Societal and philosophical implications. The notion that we may not be alone in the universe has profound societal implications. Dr. Madhusudhan's assertion that this moment could be pivotal in addressing the question of whether we are alone represents a significant philosophical leap. Significance: such discoveries challenge our understanding of humanity's place in the cosmos. They encourage a re-evaluation of philosophical and ethical considerations regarding life intelligence and our responsibilities as stewards of our own planet and potentially others. 6. Need for interdisciplinary collaboration. The discussions surrounding the findings from K2-18b highlight the necessity for interdisciplinary collaboration among astronomers, chemists, biologists, and ethicists. Understanding the implications of these findings requires expertise from various fields. Significance: a collaborative approach will enrich the analysis of biosignatures and their implications for life beyond Earth. It will also ensure that ethical considerations are integrated into the ongoing exploration of exoplanets. Conclusion: the findings regarding K2-18b represent a significant milestone in humanity's search for extraterrestrial life. While the excitement is palpable, it is essential to recognize the nuances and implications of these discoveries. The detection of potential biosignatures, the redefinition of habitable worlds, and the ethical considerations surrounding scientific communication are critical elements that should not be overlooked. As research continues, the scientific community must remain vigilant, ensuring that future explorations are grounded in robust evidence and ethical responsibility. 1. Significance of chemical signatures. The detection of dimethyl sulfide DMS and dimethyl disulfide DMDS on K2-18b represents a groundbreaking advancement in astrobiology. These compounds are primarily associated with biological processes on Earth, particularly in marine environments. The presence of these biosignatures suggests that K2-18b may harbor life, making it the first habitable exoplanet where potential signs of biological activity have been observed. This finding aligns with the broader search for extraterrestrial life, as researchers have long speculated that such molecules could serve as indicators of life beyond our solar system. 2. Hycean planet concept. The classification of K2-18b as a Hycean planet is crucial for understanding its potential for life. Hycean planets are characterized by warm oceans and hydrogen-rich atmospheres, creating conditions that could support various forms of life. This concept, proposed by Dr. Madhusudhan's team, provides a framework for studying exoplanets similar to K2-18b and underscores the importance of water as a vital ingredient for life. The ongoing research into the characteristics of Hycean planets could lead to new insights into habitability in the universe. 3. Cautious optimism in the scientific community. While the findings about K2-18b are exciting, the scientific community emphasizes a cautious approach. Leading researchers, including Dr. Madhusudhan, acknowledge the potential for geological or chemical processes to explain the detected molecules, stressing that definitive evidence of life is still needed. This balanced perspective reflects the inherent uncertainty in astrobiological research and the necessity of further studies to validate initial findings. The calls for additional research highlight the complexities of understanding life beyond Earth and the importance of rigorous scientific inquiry. 4. Implications for future research and exploration. The discoveries related to K2-18b underscore the need for continued investment in space exploration and astrobiology. The James Webb Space Telescope's role in detecting these potential biosignatures illustrates the advancements that modern technology can bring to our understanding of distant worlds. However, concerns about funding cuts to NASA's science budget raise questions about the future of such research. The ongoing exploration of K2-18b and similar exoplanets could lead to transformative discoveries, but only if resources and support for scientific endeavors are maintained. This situation highlights the interplay between politics, funding, and the pursuit of knowledge in the quest to answer fundamental questions about life in the universe. 1. The discovery of the structure of DNA. 1953, the identification of the double helix structure of DNA by James Watson and Francis Crick is a landmark event in biology that reshaped our understanding of genetics and heredity. This discovery provided the molecular basis for the transmission of genetic information and opened up new avenues for genetic research, medicine, and biotechnology. Just as the findings on K2-18b suggest potential biosignatures and the possibility of life beyond Earth, the discovery of DNA was pivotal in revealing the mechanisms of life on our own planet. 2. The Miller-Urey Experiment 1953, conducted by Stanley Miller and Harold Urey. This experiment simulated the conditions thought to be present on the early Earth and tested the chemical origins of life. The results demonstrated that organic compounds could be synthesized from inorganic precursors under conditions similar to those of the primordial Earth. This experiment sparked significant interest in astrobiology and the possibility of life elsewhere in the universe, paralleling the excitement surrounding the potential biosignatures detected on K2-18b. 3. The Viking landers on Mars 1976. NASA's Viking missions to Mars included experiments designed to detect signs of life. While the results were inconclusive, the missions ignited a long-standing interest in the search for extraterrestrial life. The cautious optimism shared by scientists regarding the findings on K2-18b echoes the discussions surrounding the Viking results, as both highlight the need for further investigation and the importance of rigorous scientific inquiry in the search for life beyond Earth. Future outlook on K2-18b, predictions and implications. The recent discovery of potential biosignatures on K2-18b marks a pivotal moment in the exploration of extraterrestrial life. As scientists continue to analyze this remarkable exoplanet, several predictions and implications can be drawn regarding its potential for harboring life and the broader impact on astrobiology. 1. Advancements in technology and research. The detection of dimethyl sulfide DMS and dimethyl disulfide DMDS on K2-18b has prompted a renewed interest in the development of advanced telescopes and instruments capable of analyzing distant exoplanet atmospheres. Over the next decade, we can expect enhanced telescopes. Upcoming missions, including the next generation of space telescopes, will be designed specifically to search for biosignatures on exoplanets. These instruments will have improved sensitivity and resolution, allowing for more detailed atmospheric studies. Laboratory simulations. Research institutions will likely invest in creating laboratory environments that mimic the conditions on Hycean planets to better understand how biological processes might operate under different atmospheric conditions. These simulations will be crucial for interpreting future findings from K2-18b and similar exoplanets. 2. Broader astrobiological implications. The findings from K2-18b will undoubtedly influence the field of astrobiology and our approach to searching for life beyond Earth. Redefining habitable zones. The concept of habitable zones may expand as we learn more about Hycean planets. K2-18b's atmospheric composition suggests that life may exist in environments previously considered inhospitable. Future research could lead to a re-evaluation of which exoplanets should be prioritized in the search for life. Focus on ocean worlds. K2-18b strengthens the argument for exploring ocean worlds within our own solar system, such as Europa and Enceladus. The potential for life in similar environments will prompt missions aimed at understanding their atmospheres and subsurface oceans. 3. International collaboration. The excitement surrounding K2-18b is likely to foster greater international collaboration in space exploration. Joint missions. Countries may come together to fund and develop joint missions targeting K2-18b and other promising exoplanets. Collaborative efforts will help pool resources, expertise, and funding, accelerating the search for extraterrestrial life. Shared data platforms. As more data is collected from various missions, the establishment of shared databases will facilitate the analysis and interpretation of findings, allowing scientists from around the world to contribute to our understanding of potential biosignatures. 4. Ethical considerations and public engagement. The implications of discovering life beyond Earth raise important ethical considerations. Responsible communication. Scientists will need to communicate findings responsibly, managing public expectations while fostering curiosity and interest. The excitement surrounding K2-18b could lead to misinformation or overhyped claims, underscoring the need for careful communication strategies. Exploration ethics. As we consider missions to investigate K2-18b or similar worlds, ethical questions about planetary protection and the potential for contamination will arise. Developing guidelines to minimize human impact on other celestial bodies will be crucial. 5. Cultural and philosophical impact. The ongoing research on K2-18b will likely influence culture and philosophy. Shifts in human perspective. The potential for life beyond Earth may lead to a profound shift in humanity's self-perception and understanding of our place in the universe. This discovery could propel philosophical discussions about life, consciousness, and the nature of existence. Inspiration for future generations. The search for extraterrestrial life, particularly through the lens of K2-18b, will inspire future generations of scientists, artists, and thinkers. The narrative of exploring the cosmos and seeking life will become an integral part of human culture. Conclusion. The discoveries surrounding K2-18b represent not just a scientific breakthrough but a transformative moment for humanity. As we stand on the brink of potentially confirming the existence of extraterrestrial life, the future looks promising. With advancements in technology, collaborative efforts, and a mindful approach to exploration, we may soon unlock the mysteries of K2-18b and perhaps find that we are not alone in the universe. The implications of these findings will resonate across science, culture, and philosophy, shaping humanity's journey into the cosmos for years to come.